All right, today we're going on a journey. We're diving into a world that is all around us, but completely invisible. A world where the basic rules of physics seem to, well, bend. And where we can rearrange the building blocks of the universe almost like they're Legos. Yep, we're talking about nanotechnology.
So let's just jump right in with the biggest question of all, the one that really drives this whole field. How on earth do you build something you can't even see? I mean, it sounds like something straight out of science fiction, but it's one of the most exciting frontiers in science today.
To even begin to wrap our heads around this, we have to think small, like impossibly small. The word nano actually comes from the Greek word for dwarf, and it means 1/1000th. A nanometer is 1/1000th of a meter. To put that in perspective for you, a single strand of your hair is about 80,000 nanometers wide. We're operating on a scale that is just, yeah, it's mind-boggling.
So what exactly is nanotechnology then? Well, the simple answer is it's engineering, but on the scale of individual atoms and molecules. It's not just about looking at this tiny world. It's about actively designing, creating, and using materials by controlling them literally atom by atom. You know, this idea isn't exactly new. The famous physicist Richard Feynman was talking about this way back in 1959. But it took until 1974 for someone to actually coin the term nanotechnology. And it was really in the 1980s that things exploded, when we finally invented the tools to make these wild ideas a reality. That's when the revolution truly began.
Okay, so let's step into this world. We are officially at the nanoscale now, a realm that's defined as being between about 1 and 100 nanometers. And it's down here, in this tiny, tiny space, that the rules we take for granted just don't seem to apply anymore. And this is where it gets really, really cool. See, when you shrink materials down to this size, they don't just become smaller versions of what they were. No, they start to behave in completely new ways. They start following a whole new set of rules. Which, of course, leads to the big question, why? Why do things that are so familiar to us, metals, insulators, you name it, start acting so bizarrely when you get them this small? Well, it pretty much boils down to two main reasons. First, you get this massive increase in surface area compared to the volume. And second, you enter the weird and wonderful world of quantum mechanics. At this scale, the normal, predictable physics of our big world gets replaced by a set of rules where things get, well, a bit strange and probabilistic. Let's tackle that first reason. Okay, so let's focus on that surface area thing. As you shrink something down, way down, more and more of its atoms end up on the surface compared to the inside. At the nanoscale, a huge chunk of a particle's atoms are right there on the outside, totally exposed and ready to react with whatever's around them. This makes them chemically hyperactive, and it completely changes how they behave. Just how different are we talking? Well, think about copper. We all know copper, right? It's a solid, opaque metal. But at the nanoscale, copper particles can become totally transparent. Or let's think about electricity. We have conductors, which let electricity flow, and insulators, which block it. Pretty simple. But down at the nanoscale, materials that are normally amazing insulators can suddenly start conducting electricity. It just completely flips their properties on their head. And sometimes the changes are even more shocking. Take a totally stable, everyday material like aluminum. At the nanoscale, it can become combustible. Yeah, the same stuff that's in your kitchen foil can become explosive if you just make the particles small enough. And this right here is a perfect visual of what we're talking about. What you're looking at is how nanoparticles of a material absorb light. Check out those two peaks. The particles that are just 2 nanometers in size absorb light at a totally different energy level than the ones that are 4 nanometers. What does that mean in the real world? It means they literally appear as different colors, and the only thing that's changed is their size. So, if materials are this different and powerful at the nanoscale, how in the world do scientists actually build with them? Let's take a look inside the nanoscale toolkit.
There are really two main ways to go about it. On one side, you have what we call top-down methods, like ball milling. It's basically a super high-tech grinder that just smashes a big piece of material into smaller and smaller bits. It's brute force. But on the other side, you have these elegant bottom-up methods, like using a high-energy laser to carefully build nanoparticles, essentially atom by atom.
The sol gel method is another one of those beautiful bottom-up techniques. You can almost think of it like a chemical recipe. You start with the right molecules floating around in a liquid, then you kick off a controlled chemical reaction,
often just by adding water, and they start to link up, forming a network, and slowly growing into particles of the exact size and shape that you want. Okay, so we figured out how to build stuff at the nanoscale. But that brings us right back to that first big question. How do we actually see what we're doing? A normal microscope isn't going to cut it, not even close. The huge breakthrough came in 1981. Two researchers at IBM, Gerd Binning and Heinrich Rohr, developed something called the scanning tunneling microscope, or STM. This was the invention that finally gave us eyes to see individual atoms, and it was so revolutionary that it won them the Nobel Prize. Now, the STM works by using a really strange quantum effect to map out atoms, but it has one big limitation. Your sample has to conduct electricity. That's where its cousin, the atomic force microscope, or AFM, comes in. Developed a few years later, it uses a teeny-tiny physical probe to literally feel the bumps of the atoms on a surface, kind of like a record player needle. And since it doesn't need electricity, the AFM can image almost anything: plastics, ceramics, even living cells. And this is the most mind-blowing part of it all. These incredible microscopes aren't just cameras. The tip of an STM is so unbelievably precise that scientists can use it to grab a single atom, pull it off a surface, and then place it exactly where they want it. We aren't just seeing atoms anymore. We are literally building with them. And I want to be clear, this is not science fiction. This technology is already changing our world. Nanotechnology is making solar cells way more efficient. It's what puts the antibacterial silver coatings on wound dressings. It's helping us get better MRI scans and creating those anti-reflection coatings on your glasses. And of course, it is the absolute heart of every single microchip in every phone, computer, and device you own. So that brings us to our final thought. For the very first time in human history, we have the tools to see, to move, and to build with the actual fundamental blocks of matter. The possibilities are, well, they're truly limitless. So the only real question left to ask is, what are we going to create next?